Hello, everybody. Welcome to our talk. Tan and I are going to talk about how to manage any layer 7 traffic in an Istio system edge. My name is Huabing Zhao. I'm a software engineer at Tencent Cloud. I've been working on microservices and system edge, particularly on Istio, for quite some time. Here at Tencent, we build a managed system edge on the cloud called TCM, Tencent Cloud Mesh, to help our customers build and manage large distributed systems. I'm more than excited to get this opportunity to share some of our findings and thoughts along the way. If you have any questions following this talk, feel free to reach out to me on Slack, Twitter, or send me an email. So people are adopting sales mesh pattern because they can solve some of the big challenges when building a microservice application, such as how to find services, how to secure the communication between services, how to get inside your services so you know what's going on, how to direct the traffic to different versions of service in our current deployment. Instead of implementing this feature in the individual services, System Edge allows us to offload this capability, this common concern, to a dedicated layer, so we can simplify the application code and focus on what we really need to focus on, the business logic. System Edge usually intercepts the traffic between services with a sidecar proxy, analyze and manipulate the request according to various traffic rules. To achieve that, the sidecar proxy needs to understand the traffic, not only on layer 3 or layer 4, but also, more importantly, on layer 7. In terms of traffic management, Istio is doing great at managing layer 7 traffic for HTTP and gRPC. But when we work with our customers, they tell us oftentimes we also have other types of layer 7 traffic in our system, and we want to manage all those traffic in a consistent way in the system edge. So in this session, I'm going to talk about a few possible ways we can extend Istio's traffic management capability to other layer 7 protocols, such as Thrift, Dubbo, Redis, MySql, etc. Then I will introduce Aeraki, an open source project which allows us to manage any layer 7 traffic in an system edge. And to give you some sense of how Aeraki works, I will demonstrate how to leverage Aeraki to do traffic splitting for a Swift application. Last but not least, Tanya will show us some very cool real-world use cases of Aeraki. Okay, let's get started. So let's take a look at a typical microservice application, like this diagram. What do we get? What kind of protocol we have in this application? We usually have a number of, sometimes even a dozen of layer 7 protocols in a microservice application. Inter-service communication is often done through RPC-style protocols, such as HTTP, gRPC, Thrift, Dubbo. In a large organization, you may even have your own proprietary RPC protocol. These services may also send and receive messages via a message broker, such as Kafka or RabbitMQ. In terms of cache, we have Redis and memory cached. We also have RDB and NoSQL database like MySql and MongoDB, etc. So when applying service mesh pattern in a microservice application, what do we expect from a service mesh? Ideally, we want to manage the traffic of all the protocols, RPC messaging cache database in a consistent way in our service mesh, not just only HTTP and gRPC. We want to distribute the request from one downstream collection to multiple upstream, so we can balance the node among multiple service instances. We want to route traffic based on layer 7 header for current deployment. We want to inject error code in the response to test the resilience of our application. We want application layer security, such as JWT authentication in the HTTP header, or authenticated to a Redis server on behalf of the client. So all this needs to be done on layer 7, which means we need to look into the TCP package and operate at layer 7 headers. So let's see what can we get for this protocol from Istio. For HTTP and gRPC traffic, we get all the capabilities we mentioned on the previous slide, so we're good. But for other protocols, Istio can only operate from layer 3 to layer 6, which means we can't do load balancing if multiple requests share the same collection. Routing can only be based on IP address, TCP port, or SNI. And we can only get TCP level metrics such as TCP send, receive bytes, or open and closed collection. In terms of security, we can do collection level authentication and authorization, but request level auth is impossible. In other words, we still need to handle this common concern, request routing, observability, security in the application code, because it still just can understand and operate at layer 7 for those protocols. So what we want is that we want to manage those protocols at layer 7. Let's say that we are running the booking for application in an Istio system edge, but the inter-services communication are done by gRPC, our own RPC protocol, instead of HTTP. So how could we achieve layer 7 traffic management for gRPC in Istio? For example, how to route the traffic to different versions of the review services based on the user lane in the request header, like this diagram shows. The most straightforward way is to directly change the pattern code to add gRPC support to the Istio. In order to route the traffic, first we need to support gRPC protocol in the virtual service CRD. In the CRD specification, we should have gRPC instead of HTTP here, and we have a routing rule called canary route, which matches the user header in the request. And if the value of the user header is JSON, then we send a request to the subset ver2. Otherwise, the request goes to version 1. So if you are familiar with the virtual service CRD, you can see that the virtual service configuration for gRPC looks just like an ordinary HTTP virtual service. That's because they are both RPCs, so they have similar semantics. They both have header and have some value in the header, and we can route the traffic based on the value of the header. So we can use the same YAML structure for both of them. Then we need to put an gRPC TCP filter in the filter chain of the listener and generate the gRPC related configuration in the pattern code for envoy. Then pattern will send the generated envoy configuration to the all the envoy sidecar in the data plane. So that's it. We can say that it's relatively easy to add support for the new gRPC protocol to the control plane. Given that the envoy filter is already there, it's already supported. But unfortunately, you have to maintain your own fork of Istio, which requires some extra effort. And we know that Istio evolves pretty quickly, so you should keep a close eye on Istio upstream and align your fork with it to keep your service mesh up to date to the latest version of Istio. If you don't like the idea of maintaining your own fork of Istio, an alternative way is leveraging envoy filter CRD, by which we can apply a patch to the original envoy configuration generated by Pilot. For those folks who are not familiar with Onward Filter, it's a powerful low-level Istio configuration CRD. We know that Istio has some high-level CRDs that are user-facing, like sales entry, virtual services, and destination rule. Pilot takes these high-level CRDs and translates them into the actual envoy configuration, like listener, route, cluster, and virtual host. We can use Onward Filter to modify the generated configuration before they are pushed to the Onward in the data plane. Basically, you can use the match condition to select a specific part of the output configuration and modify it to whatever you like. It's a very powerful tool, but it also can easily break things because Pilot cannot do much validation to the structure, to the content you have modified. Because Pilot doesn't understand OSN-RPC protocol, so it just puts a TCP proxy in the listener field chain to handle the OSN-RPC traffic. What we could do is that we could create an Istio Onward filter where its match condition is to match the TCP proxy in the filter chain of listener, and its operation is to replace the matched TCP proxy with an OSN-RPC filter. Pilot will apply that Onward filter and propagate the merged configuration to Onward. Let's look at a concrete example of Onward filter. As this diagram shows, we have two Swift services listening on port 9090, and we want to send 30% of traffic to server 1 and 70% of traffic to server 2. So what could we achieve with this use case by leveraging Onward filter? First, we need to create an Onward filter with the match condition targeting on the TCP proxy in the outbound listener, Swift sample server VIP 9090. And Onward filter supports various operations to be applied on the matched configuration, including add, remove, merge, replace, etc. In this use case, what we need to do is that we need to replace the matched TCP proxy with our Swift proxy. So we set operation to replace here. And we also set the routing policy in this Swift proxy to say that, okay, we want to split traffic to different version of server. Similarly, we also create another Onward filter at the server side Onward, which will replace the TCP proxy in the inbound listener. The inside structure of this Swift proxy is simpler here because we don't need any routing policy or special configuration on the server side. So as you can see, what we could do is that we could use an Onward filter that takes the output configuration of Istio to replace the default TCP proxy with our correctly configured Swift proxy. But there are some serious problems here. First, you have to be quite familiar with how Pilot translates these high-level HTTP into Onward configuration. You need to know the exact structure of the output configuration generated by Pilot, so you can know how to write the match condition of the Onward filter that could successfully select the correct TCP proxy that you want to replace. This structure, like listener, filter chain, cluster, they may change as the Istio evolve to new version. So the Onward filter that works in the old version could break in the new versions. You also have to know all the travel details in the low-level Onward configuration in the Swift proxy, like the type, the protocol, the route configuration. So you know how to write the patch part of the Onward filter. To make things worse, some parts of Onward filter, such as listener nerd, depends on cluster-specific information, like sales cluster IP, which means the Onward filter can't be ported across multiple clusters without modification, or need to be updated after service has been recreated. Istio can only do very basic validation to Onward filter, so you can easily break things and cause an outage. Due to all these problems, you can say that it's very difficult, if not possible, to manually create and maintain this Onward filter, especially in a large service mesh where we have dozens, hundreds, or even thousands of services. Onward filter is fragile, easy to break things, difficult to maintain, and hard to move across clusters. So you may want to use a component that can automate that process for you. That's why we create Aeraki. Aeraki is a Greek word for breeze. You can think of Aeraki as the controller to automate the creation of Onward configuration for layer 7 protocol. Aeraki pulls service entries from Istio service registry, translate the service entries combined with Aeraki traffic rules to Onward configuration, and sends the configuration back to Istio through Istio Onward Filter CRD. We hope that this breeze can help Istio sail a little bit farther to allow Istio manage any layer 7 traffic other than just HTTP and gRPC. Aeraki has the following advantages compared with current approaches. It doesn't touch the Istio code, which means you don't have to maintain a fork of Istio. It is deployed as a standalone component in the control plane and can be easily integrated with Istio as a plugin, just with a few lines in the Istio-D configuration. It provides an abstract layer on top of the Onward configuration. You can create traffic rules with Aeraki CRD, which hides the trivial details of the low-level Onward configuration from the operation. Protocol-related Onward configuration are now generated by the Aeraki, significantly reducing the effort to manage the traffic of those protocols in a service mesh. It's quite easy to control the traffic by using Aeraki CRDs. If you want to do like some advanced traffic management, such as carrier deployment, Aeraki just uses the virtual services and the distinct rule for most of the RPC protocols, such as Thrift, Dubbo, because for those RPC protocols, their semantics are similar to HTTP. For the protocol that cannot be put into virtual service and distinct rules, we define some new CRDs for them, such as Redis. The following protocols have already been supported by Aeraki, Thrift, Dubbo, gRPC, Redis, Kafka, Zookeeper, and more protocols are on the way. Similar to Istio, in Aeraki, the protocol of the service is identified by the length of the port. For example, our Thrift service port is named as TCP-Thrift-service. We should keep TCP at the beginning of the name, because from the standpoint of Istio, it's just a plain TCP service. And Aeraki will honor the following name of the layer 7 protocol and replace the TCP proxy with an Onward filter specified by that protocol. You can visit github.com/Aeraki-framework/Aeraki to get more information of this project. Let's see how could we leverage Aeraki to manage Thrift traffic. You need to prefix the port name with TCP-Thrift. Istio will create our TCP proxy for this service in the output Onward configuration. And Aeraki is going to replace the TCP proxy with our Thrift proxy. For the traffic splitting use case we mentioned before, we can use our virtual service CRD to send the content request to the two subsets with the configured weight. Redis is a bit special because it's not RPC, and its semantic is different from HTTP or gRPC. So we can't use Istio virtual service and destination rule for Redis. Aeraki defines Redis service and Redis destination CRD to abstract the trivial Redis Onward configuration from you. Leveraging these CRDs, you could offload the Redis operation from the client code to the Onward sidecar, including data sharding, read-write splitting, traffic mirroring, authentication, etc.
Okay, I'm not gonna dive too deep into these Aeraki SRDs. Tanya will give us some more real-world use cases later. Okay, let's dive into the demo. To run this demo, we need a Kubernetes cluster that has Istio 1.8 preview profile installed. And you will also want to install Aeraki to manage Thrift and Dubbo traffic. To save your time, I already have all the control plane components and demo application installed in my cluster. You can see here, I have Aeraki and Istio installed in the Istio system, and I also have a Dubbo application in the Dubbo namespace, a Thrift demo application in the Thrift namespace. For each demo type application, we have a client. We also have two versions of servers, so we can demonstrate how the traffic are routing between different versions of server. So if we take a look at the config dump of the Onward sidecar, we can see there is a Thrift proxy in the listener, in the outbound listener of the client. So by default, it will be a TCP proxy generated by Istio, but Aeraki will generate the Thrift proxy or a Thrift service. So we can see the default load is just send the account request to this cluster, and now we have two versions of server in this cluster, V1 and V2. Let's verify that. So if we take a look at the output of the client, the demo client, we can see the response are from two versions of server, the version 1 and version 2, and the request are forwarded by this inverted card to the server equally to version 1 and version 2, because we don't have any rotten rules right now. So the default load balancing policy of the inverted card is just like a 15%, 50% on loading. Okay, let's try to add a routing rule. Okay, this is virtual services. So we use virtual service to represent the routing rule of Thrift. In this virtual service, we can say that all the traffic will be sent to version 1 of the Thrift server. Of course, we have a distinct rule to represent different versions of these services. So let's try to apply our virtual services to route the traffic to only version 1 of the server. So we have virtual service here. Okay. You can see that request from the client to this host will be forwarded to version 1 of the server. So let's try to apply it. I need a few seconds to take effect. Okay, the client has been disconnected by the new proxy because we don't have RDS yet. We need to rebuild the listener. Now we can see that all the response are from the version 1 server. Okay, let's try route the client to version 2. Now all the requests from the client are forwarded to the version 2 server by the Onward sidecar. Then let's try traffic split. Okay, we have a splitting rule here. So we want to load 30% of the traffic to version 1 and 70% of the traffic to version 2. Okay, from the output of the client, we can see roughly 30% of the traffic has been routed to version 1, and 70% of the traffic has been routed to version 2. So all this traffic behaves exactly as what we intended to do. If you want to experiment on Aeraki, you can also go to the online live demo. So you can see all the applications deployed in the test cluster. You can see here we have collected all the metrics of various protocols like Thrift, Dubbo, Zookeeper, gRPC, etc. If you would like to give it a try, just as simple as 2 commands. Clone the GitHub repository and run this script. Okay, that's all from my side. Now I will hand over to Tangyang. He's going to talk about some cool use cases of Aeraki.
Hi everyone, I'm Tangyang. I'm a software engineer at Zhihu. Today, let me share with you how to use Aeraki to enhance your service mesh. The picture shows the common software architecture for most applications. There are database, cache, asynchronous communication, and RPC. It's still focused on RPC or HTTP, but Aeraki carries the left part. Database cache, message queue system, etc. Let me show you that. Div Pro Parity. Aeraki allows your application to use the same data source name, the same URL, or other information to access resources in multiple environments, such as Redis, MySql, etc. This keeps the div environment parity with the production environment. Here is an example. The application's Redis traffic is managed by Aeraki. In all environments, the applications access the actual Redis by Aeraki's Redis service. It only knows the name of Redis, user cache. Generally speaking, Redis here may be provided by any cloud vendor. In different environments, their addresses are not the same. In order to keep the same host between all environments, we could use a service without selectors. Like the YAML shown on the right, we define a service and an endpoint, and then we put the Redis addresses here. Next, we create Redis service and Redis destination to eliminate the difference between passwords or between usernames. And you can also use the Kubernetes secret here to store your Redis password instead of just the Redis password here. Maybe more safety. And if you are using a Redis operator, this can be created automatically. Here is the pseudocode before and after we use Aeraki. On the left, there are 3 configurations to record the Redis addresses and passwords for different environments, like div, staging, and pro. But on the left, we don't need configuration, so it reduces the complexity of configuration management. It can be seen that developers don't need to know the Redis password. So maybe it can avoid leaking Redis password in log or other. More secret. Aeraki gives your application more protections, like managing authorization for other systems, like databases, caches, and upgrading other traffic to MTLS. Avoiding authentication in your code. Look at this picture. There is an abstract Redis. It's managed by Aeraki. When application accesses the Redis, Envoy will automatically complete authentication with the real upstream Redis, and it's MTLS protected. Now we will talk about how the Aeraki help you to use heterogeneous databases. There are many heterogeneous databases or database proxies that use the same protocol. For example, MariaDB, TiDB, OceanBase, Aurora, Kinshard, and so on use the MySql protocol. Well, Twin Proxy, Codex, 10 days, Pika, etc. use the Redis protocol. When we want to use a heterogeneous database to replace the currently used database, like you have a MariaDB, but you want to migrate to TiDB, you maybe will ask 3 questions. How about the performance, the compatibility, and easy migration? They're very important for you. Through the database traffic mirroring capabilities provided by Aeraki, we can use production traffic to test compatibility and performance of heterogeneous databases. For cache, it's even possible to directly use mirroring to complete the double write work. Here is an example. The application originally used a single Redis instance and expected to use Twin Proxy for horizontal expansion. By using Aeraki to mirror traffic, we could use production traffic to know the performance differences between the heterogeneous databases before migration. Like the right part of this page, We can see the panel here. To know the latency gap between Redis and Twin Proxy. Next, we talk about fault injection. Istio can perform fault injection on a lot of services. This is really cool, but it's not enough. In distributed systems like database, cache, and message queue system are not always available either. So, Aeraki can help the chaos engineering system work better by providing more fault injection points, like aborting cache write, increasing database latency, etc. We've already talked about deep prod parity, security, heterogeneous databases, fault injection. I think Aeraki is very powerful. You should try. Okay, that's all. Thank you.